So today we will discuss in detail about how to find eigenvalue of a given matrix or a given transformation. And in next class, actually, I will discuss about how to find eigenvector, because even finding eigenvalue, it is one kind of solving polynomial equation. So in your high school, you might have already seen how to solve a quality equation, and linear equation is very easy to solve. So suppose you are having a quality equation, then there is a universal formula. Through that easily you can get solution or root of that quality equations. For simplicity, I am taking a general quality equation: a lambda square b lambda plus c. So it is a quality equation in lambda. So if you go in general formula, what is the root of this quality equation? You can say that it is a what, minus b plus minus there would be two root, at most two root. It would have uh, b square minus 4ac. So this general formula you know from your high school, how to find root of a quadratic equation. But if you go to find a cubic, then in general there is no specific formula. There are few technique are there, Cardan's method and other kind of technique. Uh, so those method, actually I won't go in detail how to solve a polynomial kind of equation, but what we what I will discuss few special kind of equations uh, which can be reduced to linear factor. And once we are able to factor a given polynomial into linear factor, then from there easily we can visualize uh, roots of that given polynomial equation. Okay, that is the concept. And few more technique also in general I will talk about that. Suppose you are having a polynomial of degree n. So general polynomial you will denote it like this way: n naught into lambda to the power n a1 into lambda to the power n minus 1. Likewise, you will keep on going up to last term. You can call it, last term would be constant term. I'm calling that n. Okay, so this one is the polynomial equation. And if I'm asking from the fundamental theorem of abstract algebra, what does it say? It says that it is having at most n solution. So at most n real solution. But if you take if you are asking for if you include complex solution as well, then in that case this system will have exactly n solution. So if you look for complex solution as well, so what is another name of complex field? We generally we field kind of concept, it is coming from abstract algebra. I am not going to cover that in detail. So field is simply, it is collection of real number scalars. So scalars may be complex or scalars may be real. So generally we see real kind of scalars or real kind of entries. So if you are taking your field is that means your scalars are happens to be or coefficient, only you are taking real and you need only real root. In that case you can say that this polynomial equation will have at most an real root. So that is the concept, at most and real root. Like if I consider an real root or zero, whatever you call it. So if suppose I am taking a quadratic equation like this way, lambda square plus 1. Tell me how many root this one is having. That means how many solutions this polynomial equation is having, quadratic equation. Anyone, would you like to answer? How many real root this equation is having? Yes, it is a high school problem. Okay, Satvik, you answer. How many root lambda square plus 1 is having equal to 0? Satvik, are you listening me? Okay. Naveen, are you able to listen me? If you are listening, just try to answer. Otherwise I will put you in absent. Okay, fine. If you don't want to answer, it's fine. I assume that you are absent. So here lambda square plus 1, if you take this quadratic polynomial, then this easily you can say that this one is having no real solution. It is having no real solution. But if you want to see solution from complex perspective, then there are two complex solutions. One is iota, another one is negative of iota. Imaginary roots, you got imaginary root for this one. These are actually complex number. These are not real number. If I take another quadratic equation like lambda square minus 1, then definitely it is having two solution, two real solution. One is what? One, another one is minus 1. Likewise, if I am taking a quadratic equation, cubic equation, uh, lambda cube minus 3 3 times uh, lambda 3 times lambda. Simply I am taking like this way. So how many root it will have? So it will have at most 3 root, real root, but it is guaranteed that at least one real root definitely it will have. If you are taking a cubic polynomial, it is just very much certain that at least one real root definitely you will get it. So here luckily what you observe that if you take lambda common, then you observe here lambda into lambda square minus 3. So this cubic polynomial is having three roots, three real root. One is 0, another one is uh, a square root of 3, another one is, last one is what? Negative of a square root of 3. So you observe three real root. But if I am taking another kind of polynomial, cubic polynomial like this way, lambda cube plus 3 times of lambda. So how many real solutions this will have? It is very much certain that one real solution you will definitely get here. That would be 0. That take lambda common, so your factor would be what? It would be factor into lambda square plus 3 equal to 0. And if you solve this one, then you will get only one real root. That one is 0. About other roots are happens to be complex root. So we are not worrying, we are not caring about complex root. We should not here in this linear algebra we want go for complex root. Right now only just a real root we will look for that. So in that case we say that this cubic polynomial is having only one real root, and this cubic polynomial is having uh, three real root. So in case of so simply you can say that if you are taking a polynomial of degree n, then if n is odd, then there is a guarantee that you will get at least one real root. But suppose if your polynomial is even degree, that means if n is even, then in that case you may not get any real root. So if n is even, there is a possibility that there will be no real root. But if n is odd, definitely it is saying that at least one real root you will get. So that's way if you take a matrix of size 3 by 3, then there is a guarantee that you will get at least one real eigenvalue. So at least one real root in case of odd degree. Okay, so that is the concept of solving polynomial equation kind of things. So those things will be needed here in order to find eigenvalue, eigenvector. So you just recall from your high school. In high school, you have seen enough quadratic equation, and also a standard way of by heat and trial method. Also, you can solve few higher degree polynomial equation as well. So those things just you need to recall it here. Uh, it will not you will not see very complicated kind of polynomial. Very simple kind of polynomial would be here, and easily you can get solution of that. Otherwise in MATLAB and R there are already existing command, through that you can easily calculate eigenvalue and eigenvector of a given matrix. So first part of today's lecture, I will give a recap of again geometrical motivation of the eigenvalue and eigenvector. Then I will talk about how to find eigenvalue of a given matrix. Then I will talk. So here this I am calling a finding eigenvector. I am taking as a recap. I will talk in next class, because this one is the second part is itself taking, it will take a lot of time to come. So coming to recap, in last class I had told that there are many geometrical or linear transformations that what we had already seen. So in those geometrical operation or transformation, you observe that few vector, they are not changing the direction after applying the transformation. So if you apply such kind of if you apply a transformation over very specific kind of vector, then it is just changing the magnitude but not changing the direction. So one example I had already told that if you are taking reflection kind of operation, so reflection with respect to line in R2. So take a line, suppose this one is the line, given line L, and what you do, but you don't know about the equation of this line right now. This line is unknown to you, and you do define reflection of any arbitrary point from R2 with respect to this line. So reflection of this x with respect to this line would be what? Would be this point. So call the, suppose this one is x, then this would be t of x. That means here t is a reflection transformation. So you get reflected here. And if you take any point from the line itself, then reflection of that point with respect to that line would be the point in the line itself. So you won't see any change with respect to this transformation if you are taking the point, suppose call it v. If you are taking any vector v from the line, then what you observe that it is not changing the direction of vector. So tv equal to some scalar time of v kind of things you will observe. Also there are few other kind of vectors are also coming other than along this line. So what are those vectors? So suppose you take a vector along this line. So what is name of this line? This line is actually orthogonal complement of the, the given line L. Okay, so if you take any vector, call it W, and if you want to get reflection of W with respect to this line, then what would be reflection of W with respect to this line? It would be this point. So we observe that if you are taking W from L perp, then TW is again coming in L perp. It is not leaving the direction. It is in the same line. So that's way what we say here. What these are also very special kind of vector which preserve direction of the vector. So here you can see that t of w, it just becomes lambda times call it lambda 2 times w, and here this one call it lambda 1. So here for this kind of vector, just write it freshly. I am writing it here. So t of w, if you take w from along this line, that means L per, then image of w would be what? It would be lambda 2 times w. And one more thing also, you can say that what would be sign of lambda 2? Sign of lambda 2, definitely it would be negative. Why? Because this one is, suppose we consider this one is the positive direction, then if you do 180 degree phase change, then what is meaning of 180 degree phase change? That one is talking about negative direction. So that's where lambda 2 would be negative here. And here if you come to see here lambda 1, what would be lambda 1 here? Also you can talk about sign of lambda 1 as well. So lambda 1 is, it would be positive here. So that is the criteria. That means here this v would be a eigenvector. You can call it first eigenvector, and lambda 1 would be first eigenvalue, and lambda 2 is second eigenvalue, and w you can say that second eigenvector. That is the criteria of geometry visualizing eigenvector and eigenvalue. So consider we had already discussed this one. Consider a linear transformation whose matrix is this one. So having first row 4 3, second row is 3 minus 4. So if you see this matrix closely, actually this matrix is 5 times 0.8, 0.6, 0.6 minus or negative zero point 0.8. Okay, so this matrix is actually reflection matrix. That's why I had taken this reflection operator. So clearly from the matrix perspective, you can say that the transformation is it is a reflection talking about with respect to some line, but we don't know about that line. Okay, and what we do, we observe this transformation is reflection with respect to some line, as well as it also do a scaling by factor 5. Okay, so if you take any vector from the line L and you apply the transformation, then what would happen? It will not change the direction of the vector v, just it will scale the vector by a amount of 5. So that's why t of v equal to 5 times v. That means same thing, you can write it like this way, because A is the matrix of T. So T of V equal to 5 times V. You can write it like this way: 8 times V equal to 5V. Now, once it is coming in the in this matrix form, then we call this one is what? It is a system of linear equation. And what is unknown things? V is unknown things. And in one way, we can say that V is one vector on the line, or simply also we can say that V is one of the direction of L. It is just, you can say that V is a direction of L, or it will give a basis vector for L. So we need to solve this equation AV equal to 5 times is just, so this one was the solution process. And after solving, reducing into in this reduced form, you will come across that the solution space of this system is nothing, just it is a linear span of the vector 3 1. So you got the solution space of this system. So you can say that this given linear transformation is talking about reflection with respect to the line is which is having direction 3 1. Okay, so it is geometrically very much clear that if you take any vector from the line itself, then the reflection with respect to line would be the vector itself. It is not going to change the direction. So that's way 3 1, it is invariant with respect to this matrix. That means when you apply matrix A over uh, this vector 3 1, then the operation is direction invariant. So that's why 3 1 is a very special kind of vector with respect to this matrix. If you change the matrix, then 3 1 would be not a special vector for V. Something else will be a special vector. So right now here once one transformation is given, so that's why A is fixed. So 3 1 is a special vector for uh, A in such a way. If you apply A over 3 1, you observe just a scaling, you don't observe any change in direction. So it is just 5 times 3 1. So that's where 3 1 we are calling it, it is a eigenvector of A. And the 5, the factor 5, a scalar factor what we getting here, we are calling it eigenvalue. Similarly, if you take any vector which is in the orthogonal complement of this line, that means orthogonal complement means that vector would be perpendicular to every linear combination of 3 1. So what kind of vector those are? Those vector happens to be -1 3, like this way. So this is the vector along this direction. So if you multiply A with this one, again you will observe that it would be some scalar multiple of -1 3. So you say that you got another special kind of vector -1 3, which preserve its direction when you apply matrix A over this one. So that's why -1 3 is another eigenvector. So what you observe here is this matrix is 2 by 2 matrix. That means it defines a map or transformation from R2 to R2. So what is meaning of that? It says that maximum number of eigenvector for a given matrix you will get, it depends upon dimension of the space involved. So in for a given n by n matrix, maximum number of eigenvector would be n. So here n equal to 2, so and you got 2 eigenvectors, so that one is job is done. That means you can't get more than 2 eigenvector, but you remember that if you take any, so I will talk in detail. So there are only 2 kind of eigenvector. One kind of eigenvector are coming in this line, another kind of eigenvectors are coming in this line. That means any vector on the line is acting as an eigenvector, and any vector on the in this line is also acting like eigenvector of another kind. So you are having 2 different kind of eigenvector. Okay, so a scalar multiple of an eigenvector is again eigenvector, so that one is not creating any issue. So from the definition you will see all those things. So if you want to willing to verify this concept, I have already mentioned that if you multiply a with minus 1 3, definitely it would be a scalar multiple of minus 1 3. So just validate this one. That means your matrix is what, 4, first row is 4 3, second row is 3 minus 4. Okay, and you are multiplying this matrix with the given vector minus 1 3. So what is the resultant? You can easily calculate it like this way. So 4 times minus 1 plus 9, that means 5. Okay, and next you will be minus 3 minus 12, that means minus 15 will come. Total is minus 15. So 5 is common in the both argument, so you can take minus 5 common. Take minus 5 common in order to get minus 1 3. Okay, so what you observe, that you can easily observe that here if you apply matrix over minus 1 3, you observe that there is no change in direction, just it is a scalar multiple of minus 1 3. So that's where minus 5 is another eigenvalue, and minus 1 3 is another kind of eigenvector. One kind of eigenvector is 3 1, another kind of eigenvector is minus 1 3. So that is the concept of geometrical visualization of eigenvalue and eigenvector. Okay, so one more general, that one was the case for reflection. If you are taking any general vector, a general transformation T in over R2, and this is the matrix. So this matrix clearly you can't say this matrix whether it is a reflection or projection or rotation or any simple geometrical structure. You can't say about that. So it is very general kind of 2 by 2 matrix. So what we will do if such kind of scenario is there, then we will consider that definitely it also defines it will have eigenvalue, eigenvector. So we consider that we are taking any general point, and we consider that uh, that this point it preserves direction when we apply a over b, and that preservance it is coming with respect to lambda. That means we are saying a v equal to lambda time v. In that process we are getting this system. Okay, so it is a system which involve lambda as a parameter, and we don't know lambda here, it can take any value. So we will try to substitute different value of lambda in order to get a situation where we will observe a specific kind of vector which preserve operation. So suppose if you take lambda equal to 9. Okay, so then you will get your this system, it will take this form. And what is the solution space of this system for lambda equal to 9? Solution space is just coming as a linear combination of or linear span of the vector 1 2. That means direction 1 2. So what will happen that this 1 2 is a special vector. That means when you apply matrix over this vector, call it first by v1. Okay, if you apply matrix over v1, then a times v1 would be what? It would be just equal to 9 times v1, some scalar time v1. So a times v1 would be some scalar time v1. Similarly, if you take lambda equal to minus 1, then this system will take this form. Okay, and solution expression of this system would be what? It is a linear span of negative to 1. Okay, and call this vector v2. So what you will observe that when you apply matrix over v2, then you will observe that it is again not changing the direction. It is just lambda times v2. Even lambda, you know about that. What is lambda here? Lambda would be -1. So just this kind of geometric visualization you observe. So a time v2 is equal to negative of v2. Okay, so again it is not changing the direction. So such kind of scenario, that's why v2, this a special kind of vector negative to 1, it is an eigenvector of this given transformation or matrix, and also 1 2 is also another kind of eigenvector for this given matrix. So these are the geometrical visualization, and also I had given the definition. That means eigenvector. First, we need to define eigenvector. That means what is eigenvector? It is a special kind of vector with preserved direction, and the vector must be a non-zero vector. So a non-zero vector, we will call it eigenvector if AV is a scalar multiple of just V. Okay, and that scalar we will call it eigenvalue. Geometrically, we can say that a non-zero vector is an eigenvector of A if the vector V and the resultant vector AV both happen to be parallel or on the same line. So these are the different situations. So if suppose you are taking a vector V and you multiply matrix A over V and you are getting AV, this resultant vector AV is here. So you observe here, here a scaling is happening, but there is no change in the direction, and a scaling by what factor? A scaling is happening by factor 2. So that's way 2 is the eigenvalue of this matrix A, and V is actually eigenvector. And here you observe that AV equal to V, that means a scaling factor is 1, and V is also an eigenvector with eigenvalue 1. Here you observe that if you multiply A with V, it take a 180-degree rotation phase change. So that's way V is an eigenvector of the matrix with eigenvalue negative 1. And if you take apply A over this V, what you observe, this V projected back to 0. So due to that, we say that V is again eigenvector of this operation A, matrix A with eigenvalue 0. Okay, we know that if you multiply 0 with any non-zero vector, a scalar, if you multiply a scalar 0 with any non-zero vector, then resultant is always a 0 vector. That's why eigenvalue of this matrix is 0. Okay, so further also you can observe that once you are having idea of eigenvector of a given matrix, also you can find eigenvector, and so that V would be also eigenvector of A square, A cube, even up to AK. You can keep on doing. But what will happen? V is eigenvector of all these product of A with itself, all these product. But only change would be there in case of what? This eigenvalue. So if V is eigenvalue of A and lambda is the corresponding eigenvalue, so I would like to write in pair form. So V is the eigenvalue and lambda is the corresponding eigen vector. So what will happen? Lambda square V, okay, it would be eigen pair for A square. That means lambda square is eigenvalue of A square and V is eigenvector of A square. In the similar process, you can go to talk about lambda k is the eigenvalue of A to the power k, and V is the eigenvector of A to the power k. So this, so if you are writing eigenvalue and eigenvector in together, you can call that pair eigenpair. Just for the simplicity or notation, just for the understanding point of view, you can represent this eigenpair notation. Otherwise, in no book you will get eigenpair kind of naming there. Just for your understanding, you can write it like this way. Suppose we are taking a identity matrix, n by n identity matrix. So if I ask what are the eigenvalue and eigenvector of this identity matrix, so you will observe that if you multiply identity matrix with any vector, any non-zero vector, then what happens? You are getting the same vector. It maintains the identity. So that means every non-zero vector happens to be an eigenvector of identity matrix. Every non-zero vector. But what is the eigenvalue? Eigenvalue in this case it would be 1. Eigenvalue is 1. Okay. 0. So I had already mentioned that non-zero eigenvector always must be non-zero vector. So that's why I'm not taking 0 here. And I'm taking one more example. Suppose T is a orthogonal projection into a line in R2. Then definitely T will have eigenvalue and eigenvector. It will have two eigenvalue and two eigenvector. So how we can describe? So in geometry you can observe that this is the given line and take any vector along this line. If you are taking any vector on this line, then what is the projection of v? This v with respect to this line, projection would be the v itself. Why? Because v is on the line. So that's why projection of v. If you are taking projection of any vector on the line, if you take, then it happens to be the vector itself. Projection would be the vector itself. So that's why TV equal to V is coming. It says that any vector on the line happens to be an eigenvector of this projection operator, and 1 is the eigenvalue, and corresponding that eigenvalue is what? It is 1. Now, if you take any other vector, so this one is L, this one, take any other vector which is in the orthogonal complement of L, then what is the projection of this? Projection of this one, it will directly come where? It will come at 0. If you take, even you proceed further, that means you are taking a line which is perpendicular to given line L. So if you take any point from that L per, I'm calling it L per. So what will happen? Projection of any point on the L per, it will always map to, it will be projected to 0. So if suppose if you take W is here, what would be projection of W? Projection of W would be 0 with respect to this line. So geometry, it might be visible to everyone. Okay. If you have any doubt, you can ask. Otherwise, here. So you observe like this way. So it simply says that it is also preserving the operation with eigenvalue 0. Your eigenvalue is 0. So here you got second eigenvector and second eigenvalue for this given projection, orthogonal projection operation. Okay. Further example here, rotation. If you take rotation, then rotation matrix by a angle 90 degree, it is having no real eigenvalue and neither real eigenvector. So it failed to geometry. You can observe it like this way. So why? Because if you take any vector and you apply the rotation by 90 degree, what will happen? TB will be always perpendicular to V. That means TV can't be in the direction of V. It is difficult to preserve of direction of V after doing what this kind of rotational operation or transformation. So that's way this rotational transformation is having no real eigenvalue, neither real eigenvector. So that is the criteria. Okay. So eigenvalue and eigenvector of orthogonal matrix or orthogonal linear transformation in general I will talk about. If one situation you had already seen that you take orthogonal matrix like this way 1 0 and 0 1. Like definitely it is identity matrix, but right now I am calling it it is orthogonal matrix. Why? Because column of this matrix happens to be perpendicular to each other. Also they are unit. That means the columns of A are orthonormal in nature. So what are the eigenvalue? Eigenvalue and eigenvector, every vector would be eigenvalue and eigenvector. And also, if you are taking orthogonal linear transformation, one interesting property it is having that it is preserving operator. And here you have already observed that what is the eigenvalue of this identity matrix? It is 1. So in general, if you take any orthonormal or orthogonal linear operation, what would be eigenvalue? So there are only two possible eigenvalue. There, so if only two real possible eigenvalue would be -1 and 1. And if you talk about complex eigenvalues, those would be with magnitude 1. That means it would be on the unit circle. Okay, so how you can get that relation? So simply we know that if T is an orthogonal transformation, then it preserves the length. That means the norm of TV equal to norm of P. And suppose we take a vector V which preserve direction. That means we are taking very special vector or V eigen vector kind of things. So under this situation, we will come to know that norm of lambda equal to 1. That means if you are taking a real root, so what are the real number whose modulus happens to be 1? So there are only two real number. One is -1, another one is 1. So that's a possible real eigenvalues would be -1 and 1. And otherwise, if you are willing to take complex eigenvalue, there are infinitely many complex eigenvalue whose no, modulus would be 1. What are those complex eigenvalue? You can simply denote it by e to the power I theta. So all these are complex number, and magnitude, if you try to find modulus of this one would be 1. So all these are theta varies from 0 to 2 pi. You can take it like this way. Further also you can do it like this way. So where it take theta between 0 to 2 pi. So these are a collection of complex eigen value for orthogonal linear transformation. But we are not interested. I told that we are not interested to find complex eigenvalue. We are just looking for real eigenvalue. So these are the possible real eigenvalue for orthogonal linear transformation. So one situation you can graphically you can observe that if your eigenvalue is 1, then you observe this kind of scenario. If your eigenvalue is -1, then you observe this kind of 180-degree phase change. Okay, now coming to most important part of today's lecture, that how to find eigenvalue of a given matrix. So that algorithm I will talk in detail. So consider we are having an n by n matrix, and suppose lambda is an eigenvalue of this matrix, then lambda is eigenvalue if there exists a non-zero vector v such that from the definition of eigenvector, what we know, av equal to lambda time v, and here v must be non-zero. So that's why intensely I have written here. So further you simplify, bring everything left hand side. So you write ab minus lambda time v. That means take common here, and it becomes a matrix equation like this way: a minus lambda time v into v, and where v is a non-zero vector. So now that means we are having a homogeneous equation, linear equation, a linear system. We are willing to find non-zero solution of this one. Zero is the trivial solution of this system. We are not interested to find zero solution. So we are looking for non-zero solution. That's why I keep on putting v equal to non-zero here. So when this system will have uh, non-zero solution, so only criteria is coming that when the system fail to be invertible. That means when the system is singular. That means when this is determinant of the system is equal to 0. So if you put a condition over this matrix, this coefficient matrix A minus lambda time I, that it is a singular matrix or determinant of that matrix is 0, then we can get non-zero eigenvector. So this is the criteria of getting non-zero eigenvectors. Okay, that means it is forcing v does not equal to 0. It is forcing to define this condition. So what is this? It is a, if you try to observe in a explicit form, determinant of a minus lambda equal to 0. It is nothing. It is talking about a polynomial in degree n. Why? Because the matrix is of size n by n. So in that case, this would be a polynomial of degree n, and you are equating to 0. So that's why you are getting a polynomial equation. So this polynomial equation we are calling it a characteristics equation for the given matrix. Or another name also sometimes people are calling it secular equation, but this characteristics equation is more famous. So this determinant of a minus lambda I equal to 0, we are calling it characteristic equation of the given uh, matrix. And when you will solve this equation, then that will give value of lambda or eigenvalue. So we can write the above observation as a string of equivalent statement in the next slide. You can look like this way. So if lambda is eigenvalue of A, it simply says that there exists a non-zero vector V such that AV equal to lambda times V. That means there is no change in direction. It means that you can just write it this equation like this way. That this homogeneous equation, that means A minus lambda time I into V equal to 0. So this homogeneous equation will have non-zero solution when uh, this matrix A minus lambda I happens to be singular matrix. So criteria of being a singular matrix is that what determinant of that matrix must be 0, vanishing of determinant. So this is the overall concept to uh, find eigenvalue of a given matrix. So here I will take few example. So one simple 2 by 2 matrix I have taken it here, having first row 1 2, second row 4 3. I will find eigenvalue of this matrix, and right now I am not looking for eigenvector, just I am going to find eigenvalue of this one. So first we need to define characteristic equation of this given matrix. So what would be characteristic equation of this matrix? It is determinant of A minus lambda I equal to 0, and simplify it. After simplification you will get a polynomial like this way: lambda square minus 4 lambda minus 5 equal to 0. That means it is easily you can factor it like this way: lambda minus 5 times lambda plus 1. This factorization is sometime in very layman way you can call it it is first into last method. You know from high school, I think you might have already heard first into last method. How you can factor it like this way? You factor like this way: lambda square limit. What is the coefficient of lambda square? Coefficient of lambda square is 1. What is the coefficient of lambda? Coefficient of lambda is minus 4, and constant term is minus 5. So what you do, the middle coefficient you try to break in term of coefficient of lambda square and in constant term, like so what you do here, minus 4 you try to write uh, so that's way coefficient of the lambda square call it first coefficient, and the constant term call it last coefficient. That's a first into last method, another name you can say that. So minus 4 you can write it like this way: 1 minus 5, one kind of. Okay, so 1 minus 5 is what? Again it is minus 4. So if you do that kind of representation, then then what kind of form it will take? So you are writing it lambda square minus, so minus 4 lambda you are writing like this way. You are writing it lambda uh, lambda square plus lambda minus 5 times lambda. So if you simplify lambda minus 5 times lambda, what is the resultant? Again it would be minus 4 lambda, and last term it would be as usual. Okay, now it is easy to take factor. So what are the common factor here? Here lambda is common factor, and here in the last two term 5 is the common factor. So take here lambda as a common factor. So remaining thing is what? Lambda plus 1. Okay, and in the last two term, take what is the common factor? Minus 5 is the common factor. So take minus 5 common. So remaining thing would be lambda plus 1. Okay, so now overall lambda plus 1 is common in both terms. So what you do, take lambda plus 1 common. Okay, then what are the remaining thing? Remaining thing you are having, and that means another factor you are having lambda minus 5. So this is the way to factor a polynomial if it is in very nice form. So this one is not always working good. Sometimes it is just one kind of eat and trial method. So that's where this quadratic polynomial has been factored in terms of two linear polynomial. Okay, lambda minus 5 into lambda plus 1 equal to 0. So if you solve this polynomial, what are the root? You are getting two root. One is 5, another one is minus 1. And one more thing, you remember that most positive things we will write as a first lambda. That means largest eigenvalue we will write as a first lambda, uh, first eigenvalue, then second largest and third largest. So we always try to give a proper ordering for eigenvalue. Whenever we are trying to find eigenvalue, always try to give a proper ordering. So it is not like that written. I have written this order in intensely. That means 5 is the largest eigenvalue. That's why I am taking lambda 1 equal to 5, and minus 1 is the next largest, so that's why I'm taking lambda 2 equal to minus 1. So these two are the eigenvalue of the given matrix, this. So, and we have already got eigenvalue of the given matrix. I'm taking another example, this matrix. This one is the 3 by 3 matrix. So this matrix will have how many? At most 3 eigenvalue it will have. So first job is find the characteristics equation of this one. So how can you find characteristics equation of this one? By equating determinant of a minus lambda equal to 0. Okay, that is the concept to find the eigenvalue of a given matrix. So if you are equating to 0, then this left hand side it will take a polynomial form. So it is your homework. I am directly writing polynomial of this one. What would be polynomial of this one? So there is a trick. This one is a very special kind of matrix. You can observe that what kind of matrix is this one. So characteristic polynomial of this matrix would be what? Lambda minus 2 into lambda minus 3 into lambda minus 4. So that means it is having 3 real eigenvalue. So first real eigenvalue, you can call it lambda 1 equal to 4, lambda 2 equal to 3, lambda 3 equal to 2. So you got 3 eigenvalue for this 3 by 3 matrix, given 3 by 3 matrix. So this matrix is actually upper triangle matrix. So if you are having upper triangle matrix or lower triangle matrix, then the element which are appearing along the diagonal happens to be eigenvalue of the given corresponding matrix. So that's why I had written this equation directly, and these are the eigenvalue directly you can visualize in upper triangle or lower triangle matrix. Easily you can visualize. Okay, it is already 45 minutes over. If you are having any question, you can ask. And regarding attendance, I have already created a link. Go and mark your attendance there. Thank you for attending today's lecture.